Hello everybody. Today we will study the piezoelectric materials used in transducer, the basic unit of ultrasound imaging. So let's begin with, before diving into the concept of ferromagnetism, it is crucial to understand the foundation of this phenomenon, which is ferromagnetic order. So let's first discuss what exactly is ferromagnetic order below the Curie point temperature that we will discuss. In next slide, the spins of electrons within a ferromagnetic material interact with their neighboring spins and align themselves in a specific order known as ferromagnetic order. This alignment results in all the magnetic poles within the material pointing in a particular direction. As a consequence, the material exhibits magnetization, a phenomenon referred to as ferromagnetism. Curie temperature is that critical temperature above which the randomness of the atom increases, or you can say, the temperature above which material lose their magnetic properties and intrinsic magnetic poles which were before looking in a particular direction will be disturbed and change their direction in a disordered pattern. So if we want to conclude about Curie temperature in short, we can just say Curie temperature is that point of temperature above which magnetic properties of a material will be affected or changed. Remember, Curie temperature of different materials is different. So in ferromagnetic material, all poles that we're looking before in a particular direction, on increasing the heating temperature above the Curie point or Curie temperature, then it will be converted into paramagnetic material. That is, dipoles will be disturbed and change their direction in a disordered pattern. Though above the Curie point, ferromagnetic material loses its ferromagnetism and they turn paramagnetic. However, the paramagnetic spins are still randomly aligned in a paramagnet unless external magnetic field is applied. When an external magnetic field is applied to the initial stage of paramagnetic material, all of the domains will align and it will itself become a magnet. Materials that retain their magnetism when the external field is shut off are called permanent magnets. Their domains remain aligned, and they don't need an external field to hold their domains in alignment. For example, refrigerator magnets are this type of magnet. Material that lose their magnetism once the external magnetic field is removed are called induced or temporary magnets. Their domains are only aligned in the presence of an external field and jumble up again when it is switched off. Example of temporary magnet is, if you touch a paperclip to a permanent magnet, its domains will align. But as soon as you remove the nail from the magnet, it will lose its own magnetism. Different materials have different Curie points. That is, materials have their own temperature preferences for being magnetic. This preference is called the Curie point. Each material has its own Curie point. For example, iron likes to be magnetic until it gets too hot at about 770 degrees Celsius or 1,418 degrees Fahrenheit. Curie point for a human-made piezoelectric material, which is called lead zirconate titanate, is around 350 degrees Celsius. So what actually happens if a material is heated above its Curie temperature? The result will be that there is no net dipole moment, which means that there is no overall polarization or directionality in the material. It loses its magnetic property, becoming what we call paramagnetic. As you can see in following images, vector sum for H2O is not zero. That means it has a net dipole moment, while in CO2, where vector sum is zero, there is no net dipole moment. Piezoelectric materials are fascinating substances that respond differently to mechanical stress and electrical fields. When a mechanical force or stress is applied to these materials, they bend or deform, and in response, they generate an electric charge. And when these materials are subjected to an electrical charge, they once again respond, but in a different way. They undergo deformation due to the voltage applied, and in return, they produce mechanical vibrations or sound waves. In essence, piezoelectric materials possess this remarkable ability to convert mechanical energy into electrical energy, and vice versa, making them invaluable in various applications, ranging from sensors and actuators to medical devices and beyond. There are different types of piezoelectric materials, both natural and man-made, the most well-known, and also the first piezoelectric material used is the quartz crystal. Other less commonly used natural piezoelectric materials include topaz, tourmaline, etc. Man-made piezoelectric materials include PZT, short for lead zirconate titanate, is made by combining lead and zirconium with a compound called titanate. Less commonly used man-made materials are barium titanate and lithium niobate. The advantages of man-made PZT to naturally occurring quartz are that they can produce more voltage than quartz with the same amount of applied mechanical pressure. Conversely, applying voltage to PZT provides more movement or vibration. Once a ceramic is taken to its curing point, it must never return to that temperature again. Otherwise, the material will lose its piezoelectric properties forever. For this reason, ultrasound transducers, which rely on these special ceramic materials, are never heat sterilized. When it's necessary to sterilize ultrasound transducers, they have to undergo a different process called cold sterilization. This involves using special solutions, like glutaraldehyde-based ones, such as Sedex or metricide, or non-glutaraldehyde options, like orthophthalealdehyde. However, these cold sterilizing solutions are not like regular household cleaners. They can be harmful if they touch the skin or are breathed in. That's why it's crucial to wear protective gear, like gloves and masks, when handling them. In summary, because ceramic materials used in ultrasound transducers can't handle heat sterilization, they must undergo cold sterilization instead, but handling the sterilizing solutions requires caution and protective equipment to ensure safety.